My name is Shankho Shubhra Mukherjee and I am a PhD student at Harriet University Vision Lab, and today I'll be talking about human head pose or understanding human head pose from videos. Can you all hear me? Yeah, that's fine. So, okay, so human head pose, it can give us a lot of meta information about behavior understanding and scene understanding. So what are the problems that we can solve with head pose? A lot have been talked about by Andy already. So we can understand, we can do automatic sports video analysis, like what did the referee see, our understanding behavior, passing patterns in football from gazing patterns of players. Now, another potential aspect of application is gestures versus actions. Human actions normally can be anything. I can be drinking water, but as Adam Kendon has shown, that gestures are always communicative, so it has an intended recipient. So gazing patterns are very important in not only understanding human-to-human interactions, but also in the human-robot interaction scenario, like is the person really commanding a robot or just waving his hand around? And then we move to wide area tracking of people, where outdoors people tend to look where they're going, but when they're not, that is anomalous, but that also gives us a lot of information about their behavior. And also for autonomous cars, for example, when we don't have tracking data, can we, from instantaneous head pose, predict intention, are they going to cross the road or not, and stuff like that. Also security, if people are being fidgety and looking behind their back all the time, those are anomalies that are very interesting. So very quickly, I'll show some motivating examples. This is an area in Harriet University where there's a zebra crossing and there's a door there, and there's no tracking data available. So just from the moment the person comes out, is it possible to predict whether they're going to cross the road or not? So using head pose, as you can see, it's very suggestive or indicative of whether the person wants to cross the road or wants to walk on the pavement, or actually wants to cross the road. And this data was recorded independently, so this is normal human behavior. This was not staged. Also, the next example is for sports videos. This is a huge controversy from this year's game between Newcastle United and Manchester United. Newcastle was denied a penalty, but the real question is, did the referee actually see the incident? And as you can see, in the studio, there are analysts who actually manually annotate the head pose and the gazing direction, and you can see there's an occlusion there. So these are things that can be solved automatically if we can understand human head pose from videos. This is an example of our output of our system on a football data set. Another motivating example, we can, in structured 3D environments, we can extract human visual attentions and also understand human interactions. So we're projecting their attention matrix onto the scene. Okay, so with this work, what we have tried to do is we have tried to address a few gaps that are there in the research. Well, previously all the methods of doing head pose estimation in low resolution data used a lot of motion priors, like velocity direction, which is a valid assumption because people tend to look where they're going. So in most data sets, people are following that behavior. So But like I said before, it's more important when people are not following that behavior. So we're looking to do this without any motion priors, so that the velocity direction and the head pose directions, head pose signal are not coupled, and the head pose signal itself is not attenuated by the velocity signal. Also, human-computer interaction, which is another domain where head pose or gazing direction is very important for, but humans, HCI and surveillance are treated very differently in literature with different techniques, because HCI uses landmark detection in the face, which obviously cannot be done in surveillance. And finally, all the competing methods have, like online adaptive kernel methods or Gaussian process regression, are in runtime very slow to do it in real time. Okay, so we propose to solve this problem by convolutional neural networks. And if in the past few years, if you haven't been living under a rock, I'm sure I don't need to introduce them in much detail. Okay, so the data sources we used were collected from a Kinect2 sensor. So the modalities we have, or the input channels we give to the we have are the RGB color images, the depth point cloud, not exactly the point cloud, it's the depth map, which is very different from the point cloud without the correction. And then we have the surface normal elevation angle and the surface normal azimuth angle. So these are the inputs. Okay, so when I said that we're trying to unify the problem between HCI and surveillance, the motivating factor is that the underlying generative model is the same. It's human heads. And as shown by Vetter et al. And in SIGGRAPH 99, around 400 variables are enough to capture human identity, 400 independent variables. And along with around 74 independent muscles in our face, we can capture expressions as a linear combination of around 500 variables. But of course, in real life, the problem is a bit more complicated because of occlusions like hairs, glasses, hats, and everything. But the underlying space is the images come from the same underlying generative space. So the challenges in training a convolutional neural network, as you all know, is they require a lot of data to train. And the more parameters they have, the higher the chance of overfitting. So the best models, like in the ImageNet competition, like the VGG16 from Andrew Zisserman's group in Oxford, have around 140 million parameters. But in our experiments, we found out the GoogleNet, which is a very deep architecture, but only has 5 million parameters and performs very similar to the VGG16 network, gave much better results, didn't overfit to the problem. Because to be honest, this 500 independent variables is a lot less than the natural space of images that constitutes the ImageNet challenge. Okay, so this is just an overview of the GoogleNet CNN architecture that we use. And it's a very big architecture. If you want to read up on it, you can go to their archive paper. So I'll just quickly go through the building blocks of a standard convolutional neural network. You have convolutional layers, which are linear filters that are learned, and these compute and they compute the same filter or the same filtered channel across the entire image. Then we have the downsampling or pooling layers, where you can do max pooling or average pooling. And what they do is they build up translational invariance. And then we have non-linearities in the networks that account for more expressive features from layer to layer. And at the end, we can have fully connected layers that aggregate all the things from the previous layers, and we use the loss functions like L2 loss or cross entropy for classification to train the networks and propagate the gradients and learn the parameters in the network. We made one modification to the original GoogleNet architecture where because we are doing backpropagation, one of the biggest problems we face is vanishing gradients problem. So in the original rectified linear unit that is very popular these days, the gradients vanish for while less than equals 0. So we just use the modification from Microsoft Research, suggested by Microsoft Research in 2014, and this gives us a 2.5% increase in performance. Okay, now we'll talk about multimodal combination, how we combine depth and RGB. So one way to do it would be early fusion, that is, take all the channels, concatenate them, and then feed it to the network. But in practice, it doesn't work very well. And it has been shown by Gupta et al. From Stanford, and also from our experience, that this really does not work, combining these modalities at this early stage. So we use a late fusion model where we train 2 different networks on the 2 different modalities, and then use and then concatenate the features and learn the classifier. And here are some statistics on how long it took to train the network on a GPU. If we use the Tesla K40. What's more important is that during testing, so in runtime, the network can classify 20 heads per frame at 25 frames per second, which is really real time. Okay, so what are the features that are learned by the network? So as you can see, I have highlighted here, there are filters that actually detect the facial landmarks, and also you can kind of see there are skin maps being extracted, but those are things that are very intuitive. But along with that, there are non-intuitive features there that the network learns. We would, if we were to design the features ourselves, we might not have designed for those things. So also, how good are the features? So it's a 2-dimensional embedding of the high-dimensional features. So in the competing techniques, most of the techniques used the hog features, and as you can see, it's not really well separated. And also, in our case, the connet features are very, very well separated in only 2 dimensions. But at the same time, you can see it has kind of learned the circular manifold of the head pose problem. Now we'll talk about the depth CNN features. So similar to that, the depth is actually very good in the frontal poses, near frontal poses, but the back of the head poses are kind of clustered together. So this actually tells us about limitation of the depth sensors, because we use infrared light bounced from the object to sense depth, and most of the time our hair is not very reflective, so it's very noisy, the back of the heads. Now we want to go from classification to regression. So all competing techniques, because for HCI we need very like from coarse gaze estimation of 45-degree bins in what that is the norm in surveillance domain. We want to solve the problem in a very smooth manifold. So we want to go from classification to regression. So we fine-tuned the classification networks and gave it the original ground truth angle. So we used L2 loss for regression, but unfortunately that doesn't work very well. It actually destroys the manifold, the circular manifold of the problem. The reason is the head pose does not lie in an Euclidean space, so the Euclidean error function is not optimal. Now to pose the problem, so we can write a geodesic distance function and take its derivative, but we can also solve the problem very easily by providing the components of the vector in that direction, unit vector in that direction, in the xy components, and then again it is posed in the Euclidean space, and we can compute the L2 loss. And if we do that, after training we again get back the circular manifold. And this is also very easily extendable to when we are trying to estimate both yaw and pitch angles of the head. So we just use the XYZ components of the vector. Okay, so I'll quickly show our output on the Oxford Town Center dataset. and this is instantaneous, so no smoothing is going on. And previous techniques where people are not moving, like the garbage man, it's hard to, previous techniques would fail there most of the time, because there is no motion information to smooth the head pose, or for this individual gentleman standing right there on the street.
Question. All of this work is based on using Kinect for input?
No, not all of them. So we have two separate networks, so we don't need it. So when we have depth, we can use it to improve.
Okay.
When we don't, we can just use the RGB. Okay. Oops. Okay, so also one of the good things about Gaussian process regression is that apart from regression, it also gives you a regression covariance estimate. So how do we incorporate that in our network? So we took an easy way around. So we, on top of the regression features, we trained the 360 class softmax classifier that each class spans 1 degree, and that gives us a PDF, a probability density function over all the angles. And from that, we can compute the variance. And as you can see, the depth in the HCI domain, that is less than 3 meters, both depth and RGB give us very highly confident estimation. As the distance goes up, the regression confidence of depth falls off very rapidly, whereas the degradation for RGB is much more graceful. Now we'll talk about results. Now, compared to competing techniques, that's the previous state-of-the-art Benfold algorithm on the Oxford dataset in the surveillance domain. That's their confusion matrix, and this is our confusion matrix on the same dataset. And also at the same time, this is the Caviar shopping center dataset. This is our confusion matrix. One point of interest, if you can see, their confusion matrix is highly biased towards two classes, 1 and 5, and surprisingly, not surprisingly, that's the direction of the road. Most training samples for them are walking up and down the road, and it's highly biased in the walking direction. Okay, if we compare the mean squared error in angle, so compared to other techniques, we achieve significant improvement in performance. Now, when we're combining multimodal data in the HCI domain on the BUE Kinect dataset, again, our RGBD combination in both pitch and yaw, we improve upon previous state of the art by a significant margin. So, to sum up, our main contributions in this area are unified HCI and surveillance, and so we unified both the HCI and surveillance domain. Achieved regression, so we went from coarse gaze estimation to very smooth gaze estimation, and we are also doing it in real time. So once we have solved this problem, this enables us to apply this for social signal processing and also for security better tracking in surveillance videos that I come to now. Okay. Applications. So the first application I will talk about is human attention modeling. What this is we take for, so once we have the regression of the angle and the regression confidence, that's the spread of the attention, spread of the classifier confidence, we can define an attention model which is a 3D spherical distribution called the von Mises-Fisher distribution for human attention. And from that we can compute whether two people are looking at each other or doing the same thing using windowed cross correlation, or we can project the attention map in 3D. So quick example, we're computing the interaction metric between two people, that is this multiplication of the two attention metric over the distance squared between the two people. So now the second application we have is improving tracking or human tracking, visual tracking using head pose as an intentional prior. So most of the time when we want to change our course, we tend to look in that direction first before changing course. So in the meantime, if we have some occlusions where the tracking data is not available, head pose or intentional prior gives us a much better estimate of the real trajectory than the standard Kalman filter. Like I said before, in most datasets people are looking where they're going, but when they're not, we are interested in the corner cases. So what are the results for tracking? On the Oxford Town Centre dataset, we achieve a 7.2% improvement in log likelihood compared to the standard Kalman filter, whereas in the KVR dataset we achieve a 19.5% improvement in standard log likelihood. And also we reduce the ground truth error by as much as 63%. Okay, where next? So now we're working on using fully convolutional networks for detection and also not only detection but at the same time predicting attributes of humans, all the humans in the scene. Also we are using multiple modalities for understanding human behaviors like audio and video. We're using convolutional neural networks and long short-term memory networks for that. And we're also working with Queen's University Belfast on embedding CNN and RNNs on FPGAs for smart camera applications. That's a shortlisted proposal with IBM, Xilinx, and Queen's University Belfast. And we're applying this to directly to security, social signal processing, and human-robot interaction. These are the related publications if you want to take a look, and that's it. Thank you. Questions?
I think what we're going to do is we're going to leave questions until the end of the session. Actually, then gives us actually chance to actually ask questions of all the people. But I'd like to sort of thank Rick very much for giving his talk and introduce our next
question for the first speaker. I can't pronounce your name, please.
Rick.
Rick. Good. So I just want to ask, what environment did you use to implement this deep learning? Was it Piano or Cafe, or what were you using?
Oh, the framework is Cafe, yeah.
Cafe. Okay. Interesting.
And so I'll come to you in a sec. One at the back over there.
Thank you for your talk. So could you explain how exactly you fine-tuned the existing Google Net, or did you train it from scratch?
What about you, Rick?
Okay, for the first course classification, I trained it from scratch, and then for the regression, I fine-tuned the classification network.
So did you just reuse specific layers from Google Net?
No, I didn't use, so the weights were initialized, so I just used the architecture. Okay. The weights were initialized randomly, so it's not the ImageNet trained model.
And there was one over here.
So for you again.
Oh, sorry. I'll tell you, you keep that.
Where do you get the ground truth from?
Okay, so for classification, most of the surveillance datasets that have head pose annotated is the course classification annotated, and for the regression, we gathered our own data using the Kinect.
That's good enough.
And gathered our own data, but also we used a hidden IMU sensor.
Oh, okay.
So, yeah.
Any other? Another question for Rick. Can I just, in terms of you, I think what I noticed that the actual length of time it takes to compute. I think you talked about several days in terms of computing. My question is, I mean, what are you limited by? Is it the fact that you've taken, if I was to give you a magic computer that was 100 times faster, would you still take 3 days? In other words, would you just basically use more information and data, or is it the fact that you can do well enough, and therefore the speed up? If you can actually sort of get a speed up, you can actually sort of do that much more quickly.
Okay. So the question is about the training time. Yeah, the problem with right now is it's actually an engineering problem, how to scale up training of neural networks. So we know how to do it on one machine of multiple GPUs using data parallelism and model parallelism. So if you give me, instead of one GPU, 4 GPUs, it's around 3.75 times faster. Whereas it's still the scaling, up to a cluster, it's still not optimal. So we are working on it, and we already have a cluster on order, so we'll be writing some code, and we don't know yet.